Hi, everyone. My name is Eddie Calleja. I am a software development manager for the AWS DeepRacer team. I manage the software that runs the AWS DeepRacer virtual environment, device software, and I also manage the reinforcement learning algorithms that power the AWS DeepRacer. Today, I want to talk to you about our latest release, the open sourcing of the AWS DeepRacer device software. And you may be asking, what is the AWS DeepRacer? Well, for those not familiar, the AWS DeepRacer is a 1/18 scale autonomous driving vehicle, which we've built to teach customers about reinforcement learning. You can see it here in this video that we've made for you. And you can see all cool little sensors that we're going to get into throughout the talk. I want to just point you to our 2 cameras, which allow us to do stereo sensing. And also this little hockey puck at the top, which is used for LiDAR and imaging, which allows us to image things with a 360-degree radius. So what is the mission of the AWS DeepRacer? Well, again, we really wanted to do it to teach people about reinforcement learning. And we wanted to do it in our own unique way, which is to say, to literally put machine learning in the hands of the developers. We feel this is the best way to teach people about reinforcement learning, where you can train a model and then go see what it'll actually do in the real world. So the AWS DeepRacer is the 1/18 scale autonomous car, but it turns out the way reinforcement learning works, you can't really train it in the physical world or on the car itself. If you were to try to train the model on the car itself, you'd be in for a heck of a workout. These models take anywhere from 3 hours to 24 hours to train, and reinforcement learning requires the car to do a bit of exploration. And you can think of exploration as kind of what it sounds like, which is exploring the environment. So you can imagine if you had a car that was trying to explore the environment around your house, you'd be kind of chasing it all over the place. And you'd get a great workout, but it certainly wouldn't be efficient for training. So because of that, the training happens in a virtual environment. And this is a 3D world that runs on Gazebo and ROS. And this is where you train your reinforcement learning model. Your reinforcement learning model is then deployed to the device, where you can see how successful your model worked, where you can compare how successful your model is in the virtual world, and if that transfers over to the real world. And a funny thing happened while we were developing the AWS DeepRacer back in 2018. We found that different teams were competing because, after all, it's a car, so it's only natural to want to race against each other and figure out which team could train the best reinforcement learning model. We had an absolute blast doing this. And so we thought we'd bring the fun of competing and training reinforcement learning models to see who could go the fastest to our customers. So we created the AWS DeepRacer League. The AWS DeepRacer League is a place where you can compete for prizes and glory. It happens in 2 ways. Every month, we have a virtual competition where you compete against developers from all over the world. And we also have a physical competition, which usually happens at AWS summits worldwide. The winners of these competitions get to participate in the AWS DeepRacer Championships, which happen at reInvent. If you don't want to participate in our monthly races, we've released a new feature, which is DeepRacer Community Races. These are races where you invite your friends and you compete. So you would open up what we call a leaderboard or a competition, just the same way that we do every month. But instead of competing against everybody in the whole world, you can decide to invite your friends or office mates and learn more about reinforcement learning that way while having the fun of competition. So I could probably spend the rest of this talk talking about the virtual simulator or the AWS DeepRacer League, but I want to focus on the device, because that is the code that we've decided to open source. So the AWS DeepRacer device, again, is a 1/18 scale autonomous driving car. And here are some of the specs. It runs on an Intel Atom processor. We have a stereo camera, which is the two cameras that you see here. And we have the LiDAR, which is this hockey puck feature that you see up here. We built the AWS DeepRacer on an Ubuntu 16.04.3 OS, and we used ROS Kinetic to sort of build out the infrastructure for it, or the application. And remember, with the device, what we really wanted to do was to give you a device where you could deploy the reinforcement learning models that you trained in the virtual simulator. And then the device would just take that model, run it, and you would see how well your model performs in the real world. So you wouldn't have to deal with the code or any of the robotics application that we built behind it. We took care of that for you. And here is a high-level architecture of the software that we build to run these reinforcement learning models. And so the first thing that happens is you take the model that you trained in the virtual simulator up on the AWS DeepRacer console, and you deploy it to the device. Now, when the model comes out of the console, it's not quite ready to run on the device. And this is because the console uses a powerful server to train the model, but on the device, we have less compute power. So we have to do some optimization. And we use Intel OpenVINO to do this optimization. These are common optimizations that you'll find when you run inference at the edge, such as quantization and layer fusion. The other thing that Intel OpenVINO does is that it transforms the models from a set of instructions that was running up on our service to a set of instructions that can run on the Intel GPU that powers the device. And this happens asynchronously. Once the model is optimized, it's loaded onto the GPU. And then we can get into the inference flow, which happens down here. I also want to point out that for the purposes of these diagrams, the blue boxes represents what are ROS nodes, and the orange boxes represents ROS messages. Now, ROS is a powerful middleware that is typically used in robotics application. One of the key things that it allows you to do is it almost forces you to write modular code so that you can swap in different nodes in and out. It also runs the nodes as individual processes, because you can imagine for robotics, we may want to have a process, or in the language of ROS, a node that monitors something, for example, battery life, and another process that is responsible, for example, a driver to drive the car. And yes, a driver to drive the car is a mouthful, but you find that in this business of AWS DeepRacer, we get a lot of puns. So the way these modules work is they all spin up as an individual process. And then you can think of these ROS messages as user-defined data structures that we use to send data from module to module. So the simple inference flow is that we have the sensor, and this sensor, in this case collecting images, sends them over to the media engine. And the media engine is essentially a driver which we built to collect images from the sensor, and then it emits them to anybody who's listening for these images via this video MJPEG, which is a ROS message, and it sends it to two places. One is the web server, and the web server is when we built the DeepRacer, we built a simple device console so that customers could interact with the device. And this is where you would load your models that you trained on the console. This is where you could manually control the car, for example. And this is also where you could see the video that's being sent out from the camera. And we also have visualizations around the LiDAR as well. These things tend to help with debugging a model if what you're after is what we call domain transfer, which means transferring a model from the virtual world to the real world. Now, the more interesting path is the images that get sent to the inference engine. And the inference engine is the node that processes these images, actually runs the machine learning models on them, and then sends out a result. Now, when we're talking reinforcement learning, the result is always a probability distribution. So it sends that probability distribution via the inference node, via the inference results ROS message. And then that gets received by the navigation node. Now, the navigation node is where we wrote the code to decide how to handle the probability distribution being sent out from the inference node. And this navigation node eventually decides whether we want to steer the car left, whether we want to go faster, slower. These type of decisions are what we do in the navigation node. And then that sends those decisions via the autonomous drive message, and it goes over to the control node, which is where we have the drivers that, well, drive the car. Back again to my bad joke. And so this is a high-level view of the system that we designed. And we realized that the team kind of built a competency in building these ROS applications, but you can immediately see the modularity of such an application. If I wanted to, for example, use a different navigation logic, or we use what's called a greedy policy, which means we just take whatever action has the highest probability when running a reinforcement learning model. But if we wanted to sample the distribution and have an exploration policy, we could do that by modifying the navigation node, and we could have different navigation behavior. So it really was a system that's very modular and easy to onboard with. And so we thought that a natural next step for us was open sourcing the code. And we asked ourselves, well, what are some of the reasons for open sourcing the codes? And one of it is to go beyond the track. Now, with the DeepRacer open source release, we are open sourcing all of the code that I just showed you in the previous slide of that sort of high-level architecture. And we're also giving you 6 sample projects to give you an idea of how you could use the code to build cool applications, such as the one here. So this one on the left is actually what we call Project Off-Road. And what we did is we said, well, the DeepRacer is really good at following a track, and we have some events that where we do racing around a track, and or virtual competition is around a track. Well, let's make a new kind of track. And so we built an application by modifying the core code where the car, and what you're seeing here is the camera of the DeepRacer car, and it's actually detecting different QR codes. And in each QR code, we've embedded an action. So it tells the car, hey, drive left or drive right. And so it effectively creates a sort of custom path that it can follow. So it's kind of a way for us to go beyond the track. And we also had, and this one comes from the community, a project where we attached a cannon that fires toy balls to the back of the DeepRacer, which is what you're seeing here. And this is really interesting because you could use the reinforcement learning capabilities of DeepRacer to navigate a track or a course that you set up. And then you could use this cannon and potentially even computer vision to pick out targets where you fire toy balls. So this is one of my personal favorite projects, and it was driven by our community that participated in our beta program. So along those lines, community is a big reason we wanted to open source the DeepRacer. So already, if you haven't checked out DeepRacer.io, I highly recommend it. It's an organic community that's built around knowledge sharing for reinforcement learning, where everybody shares the tips and tricks and learns together about how to build a better reinforcement learning model. So we already saw a DeepRacer community that was thriving and talking about reinforcement learning, and we saw some signs from the community about people that were tinkering with the device. Our core mission is education, and we find that education works better when it's done in a collaborative way. So driving that community engagement and engaging the community to participate in this project was a big reason that we wanted to open source the device software. And if you're going to open source something, a great place to put it is GitHub. And if you're not familiar with GitHub, I highly encourage you to go check it out. And you can check out the DeepRacer GitHub organization, which is at github.com, AWS DeepRacer. GitHub has all the tools to enable community collaboration. It's easy to share code on GitHub. There are forums and a whole set of tooling that makes GitHub the right place for the AWS DeepRacer code to live. And as we started doing this, we realized that the DeepRacer device itself actually is a pretty good robotics development hardware kit. And it has some advantages in that a lot of robotics hardware kits you have to assemble. So you can see here I've listed a picture of what it would be like if you had to assemble a DeepRacer. Some folks may look at this like lots of fun, and it is, but it's definitely something that will consume a large amount of time in putting this thing together. So with the AWS DeepRacer, if you wanted to use it to sort of build robotics applications or to develop robotics applications, you could just purchase one and pull it out of the box, and it already comes assembled. AWS DeepRacer is also very easy to on-ramp with. There's extensive documentation on how to provision the device, how to get it all set up, and it can be done fairly quickly. We also have 4 USB sensors on the device, and this allows for easy plug and play of new sensors. For example, 2 of our favorite ones are the Intel RealSense camera, if you want to do depth detection, and the Intel Neural Compute Stick, which we use to increase the compute power of the AWS DeepRacer. Both of these extra sensors or devices rather are easy to plug into the AWS DeepRacer, and you can just plug them in and play and get rolling right away. Now, when we started thinking of robotics application, if you remember a few slides ago, I told you about how we built the DeepRacer and that we used Ubuntu 16.04 and we built it on ROS 1. Well, we wanted to give customers the most and longest term support. So as part of this initiative, we've upgraded the OS to the latest Ubuntu OS of 20.04.3, which has the longest term support going forward. And we've also changed from ROS 1 to ROS 2. So why ROS 2? Well, we wanted to give customers the longest term support, and ROS 2 offers that. It's also the most secure version of ROS available. And this means that you could really use it to prototype production robotics. And we also managed to make the AWS DeepRacer one of the first robotics developer robotics hardware that is built on top of ROS 2. So ROS 2 is definitely the future, and this device gives you all of our code that you're going to see on our repository. All of our sample projects are written on ROS 2. So this is a great way to get started with ROS 2. So coming back to sort of our initial mission, which was to teach customers about reinforcement learning, open sourcing also gave us the opportunity to go further with machine learning. The initial DeepRacer was limited to reinforcement learning, but by open sourcing the software, customers can now build robotics applications that integrate with computer vision, or they can build a robotic application that uses reinforcement learning, computer vision, and even incorporates some robotics application within them. So really, it's up to you guys to figure out how you want to leverage this, in the future. And we're really excited to see what kind of ideas and what kind of combinations you come up with. So I want to focus on a sample project, which is Follow the Leader, as a way of showing you how we can do this integration. So here's what the end product looks like. So we made modifications to the AWS DeepRacer so that we could use a computer vision model to follow one of our engineers around the office. And I want to point out that although we don't see our engineer here, he doesn't have a controller in his hands. This is really being driven autonomously. And the DeepRacer is using computer vision and a tweak to the navigation node to follow him around the office. So if you're just interested in tweaking the DeepRacer follow the leader sample project, you can actually set this up without very much code. There's one thing to mention. If you already own an AWS DeepRacer, you'll have to upgrade the OS to Ubuntu 20.04. And there are instructions on how to do this online. But once you are on Ubuntu 20.04 and the latest version of the software, you can easily get started with the follow the leader application in 5 simple steps. And I just want to briefly go through them. The first step is to clone the application repository. So all we're doing here is just cloning the code that's already on GitHub. Then you want to download the model. As I mentioned, the follow the leader application uses an object detection model to detect the object that it's going to follow. And we've built a model for you. And one of the cool things, if you just want to briefly tinker, is you could just swap this model for something else if you wanted to follow something else other than one of our engineers. And then you could just run these steps again to get the application started. The next step is to grab the ROS dependencies. So another really cool thing about ROS is that a lot of these nodes, there's a lot of open source software and support around it. It has a large community of developers. And so you can build your applications on top of other open source nodes. So this bit of code here, or these shell commands, basically just grab the ROS dependencies. Step 4 is to build the software on the device. So as I mentioned, you're going to do this all on your DeepRacer device. You're going to plug in an HDMI cable and a mouse and keyboard, or you can SSH into the device depending on your preference. And then you're going to build the software. And we've provided a script to help you do that. Finally, we get to the fun part, which is step 5, which is where you launch the actual application and have the car follow you around. So that's how you would get started, just with the sample application and getting it up and running. Now, if you want to dive deeper and actually build an application like this, you have to kind of understand some of the things that are available on the AWS DeepRacer GitHub org. So we've sort of categorized the nodes that we've made available into 5 categories. And I'll start off with navigation, because this is really where a lot of the tinkering, this is a great place to start tinkering. And there's 3 navigation nodes here. We have the follow the leader navigation node, so you could take a look at how we make the car sort of follow you around. And then we have the off-road. So at the beginning, I showed you Project Off-Road that's detecting these QR codes. So you can take a look and see what navigation logic we're using there. And then there's the traditional DeepRacer navigation node. As part of the things that we classify as navigation is the servo node. And you can think of the servo node as a driver. This is the node responsible for sending pulse width modulations down into the servo. And the servo is the piece of hardware that actually allows the car to move. The next set of nodes that you'll probably want to tinker with are, we sort of classified as decision. And these are nodes that basically do the processing of data coming in through the DeepRacer. And this data is collected via sensors. And we'll get to that in just a second when we talk about perception. So the inference node is our traditional reinforcement learning node. This is built to take a reinforcement learning model and run inference on it. The QR detection node actually doesn't use machine learning. And it's one of the cool sort of robotic applications that we sort of came up with. It just uses QR detection technology, and then that's how it processes the images. And then there's the object detection node, which is different than the inference node in the sense that this node is using an object detection model. And differences between an object detection model and a reinforcement learning model is that an object detection model will draw a bounding box around the object that it detects. And so you have to process sort of that bounding box and do some geometry to figure out how much you want to move the car and to where you want to move the car to. Whereas the inference node for reinforcement learning, it doesn't have any bounding box. It just takes in the image as a state and makes a decision. So it just takes an image and decides whether it wants to move the car left or right, or rather tells you which is the best action that you want to take. So you can then move on to the perception nodes, and this is essentially drivers for sensors. So you can see that we have the RP LiDAR node. This node is responsible for collecting data from the LiDAR. And likewise, the camera node takes data from the camera. The RealSense node takes data from the RealSense. We also have an IMU on board. And so the IMU also takes data from the IMU if you wanted to use it. I'm going to talk a little bit more about the sensor fusion node in the next slide. So we see how all this stuff is put together. And then there's localization and mapping. And this is with one of our sample projects, which I haven't shown you guys, but you can check it out at the GitHub. And it's about simultaneous localization and mapping, and SLAM. And SLAM is a common technique in robotics. In our sample applications, we use it to take a 3D image of, for example, your office or your room. It's incredibly cool, and I recommend you check it out. And we provide 2 nodes to help you build out SLAM applications. And finally, there are these backbone nodes, which you'll find yourself probably not tinkering with them as much. These include a USB monitor node, where you can monitor the USB ports. And for example, when a device, or perhaps even just a USB key is inserted into the AWS DeepRacer, you get a notification and you can code it to take some action. We'll see some examples of that in the next slide. We have a node for controlling the LEDs on the back of the DeepRacer. And so this is how you would do it using the status LED node. And we also have a node for querying the battery status of the servo, which may be important if you're building an application where you want to increase the power or the pulse width modulation as battery declines. A lot of these backbone nodes sort of are standalone nodes. So let's take a look at how all of this interacts in the system and take an even deeper dive. So this is the AWS DeepRacer Evo system that runs on the device. So this is very much the software. If you bought an AWS DeepRacer and you were just using it for reinforcement learning, this is what's actually happening behind the scenes. And this diagram may look a little scary at first glance, but we'll actually see it's quite simplistic. So the first thing I want to draw your attention to is that the so-called backbone nodes, so like the status LED or the battery node, they tend to be standalone. And that's because they're just processes that are monitoring and emitting messages to whoever needs them. And you could decide to set the LED or monitor the battery status. So there's not a lot of intra-node communication. And you see that on a few things here, like the model optimizer, which we talked about earlier. It just needs to take a model, convert it, optimize it, and basically put it on the GPU. So these backbone nodes tend to be standalone nodes, but certainly if you want to connect them or use them, you're welcome to now with the open sourcing of the device. More interesting are sort of the sensor nodes. So here's our camera package, and these packages is just how Ross thinks about bundling the software together. So a package will include a node, for example, in this case, the camera node, and will also include the messages that are being used to send data to other folks that need it. So In the camera package, you have the camera node, and you have these two messages. And that's because we have two cameras. We have one on the left and one on the right. And they emit their images out, and they come over to the sensor fusion node, which is part of the sensor fusion package. And the sensor fusion node also takes data from the RP LiDAR node, which is what collects data from the LiDAR. Now, you may be asking, why does all this data need to come to a sensor fusion node? And the reason for that is because we collect data from the camera and the LiDAR at different frequencies. We collect data from the camera at 15 hertz and data from the LiDAR at 10 hertz. So therefore, we can't just send it over to the inference node to run it through our machine learning model. We have to collect this data and fuse it together, depending on how you want to define this logic, and then emit the fused data, which will then go over to the inference package. And the inference package takes the fused data, it runs it through the machine learning model, it produces inference results, just as we've talked before, and then it sends those inference results over to the navigation package. And this is the navigation node, which is where this is where you're taking the inference logic and you're deciding, hey, do I want to go left, right, forward, backwards? You then send that data out. It goes over to this control node. Now, the control node here is basically to decide which configuration the device is in. The AWS DeepRacer can run either in manual mode, where you use it as an RC car, basically, or it can run in autonomous mode, where it drives itself via the reinforcement learning model or the machine learning model. So the control node decides which input it wants to forward out to the servo node. And the servo node, as I've mentioned before, is the driver, which actually takes what you want the car to do and converts it into raw PWM, pulse width modulation. That signal then goes to the servo, and then the car moves in however you've defined your navigation. There are a couple of other things on here, just to briefly mention, which is the USB monitor package. So this is an example of how you could use this. So the USB monitor package monitors the USB ports. And one of the things that you can do on DeepRacer is that you can actually provision it using a USB, as long as you have the right file format on that USB, to point it to a particular Wi-Fi. So basically, this USB monitor node checks when you plug in a USB. If it finds the file that it's looking for, it'll try and take those Wi-Fi credentials and then connect over to the system. And this is an example of how you could use a USB monitor node and how we use it in AWS DeepRacer. There's also the web server package. And again, this has to do with the device console that we provide to you guys so you can interact with the car. So this is pretty much how this is all set up for the AWS DeepRacer device. So how do we extend it? Well, the follow the leader application takes that existing architecture and extends it. And basically, the developer only has to code two new things. So first, we talked all about the sensor fusion node. And remember, the sensor fusion here has the camera node behind it, and basically all the data comes in here. We've left that out for simplicity. But this is already existing code, so you don't have to modify it. You can just build on top of it. And likewise, the servo node, which is setting the PWM and sending the signal down, you also can just take from the open source repo, and you don't have to code anything here. So basically, you can build the follow the leader application by just developing two new nodes. You need an object detection node, which is to process an object detection model. And you can see here in the flow, we go object detection model, we have the bounding boxes, and we actually calculate the normalized delta between those bounding boxes to figure out how to steer the car. And then, as you're going to find, I think, in many applications, you need a navigation node to basically figure out which actions the car is going to take and how the car is going to interpret the data coming from the inference. And so in this case, we actually gave it an action space, which for those of you familiar with reinforcement learning, that an action space is just a set of allowable actions. We found that this was a little bit easier to navigate. So action space in this context just means that we only allow the car to take certain actions. So meaning we'll only go left by 30 degrees, right by 30 degrees, etc. So the only actions that the car can take are the ones we define in this action space. And then we plan action here by mapping the deltas between the bounding boxes and this action space. And then the rest of it is just publishing out the steering angle and speed to the servo node. And just that easily, we can leverage everything that we built for the AWS DeepRacer to extend it and build a cool application like follow the leader. And here's another example of follow the leader where we're actually going to do a 3-point turn. So you can see the engineer here backing up and going forward, and the car essentially doing a 3-point turn as it moves around. And again, all this is a custom navigation node with an object detection model where we replace the inference node with an object detection node, and we replace the navigation node with a navigation node to handle the follow the leader logic. And just like that, you can build an exciting new application. I want to also point you to various resources that you can use when you're thinking about building your AWS DeepRacer project. All of our sample projects can be found in AWS, Amazon.com, DeepRacer Robotics projects. Please go visit the GitHub and check out the code, example, and documentation, which is there. And that's over at github.com/AWS DeepRacer. Strongly recommend checking out the community IO, which is over at deepracing.io. And finally, if you want to try the original AWS DeepRacer, head over to www.awsdeepracer.com and feel free to compete in our monthly league and leaderboard event. And finally, I want to thank you for listening to me and thank you for your time today.